Okay, so a major challenge in the study of perception and action is to understand how behavior is so well coordinated with the environment on a moment-to-moment basis, so how behavior is so adaptive. And over the years, it's proven useful to approach the study of adaptive behavior from an information-based perspective, right? One that emphasizes the tight coupling between information and action, that relies on online control based on task-specific information, and one that portrays behavior as emergent. But behavior is not only adaptive, right? It's also stable and energetically efficient. And an emerging view in motor control and in many areas of robotics these days is that this stability and efficiency can be achieved by exploiting the physical dynamics of the body and the environment. So this has some pretty major implications for our understanding of the nature of the control problem that biological systems have to solve. So in a nutshell, rather than actively controlling each and every detail of a movement, biological systems can sometimes take what's given to them for free in the form of stable behavioral solutions and in the form of external forces that can be harnessed to move the body with a minimal amount of self-generated force. So one task that really begs for an analysis in terms of informational and physical constraints is walking over complex terrain, right? Because behavior is really easily characterized in terms of a tight coupling between information and action, but it's also the case that the body is a physical system with a particular structure that's best controlled in a particular way. So to appreciate this latter point, it's helpful to start with walking over flat, obstacle-free terrain, where it's pretty easy to see how aspects of walking behavior emerge naturally just from the physical dynamics of the body. All right, so back to point light displays, I guess. During the single support phase, when one leg is planted and the other leg is swinging forward, the human body is mechanically similar to an inverted pendulum. The center of mass serves as the bob of the pendulum, and it is supported over the pivot point at the ankle by the stance leg. In the idealized pendulum model, there's a perfect exchange between potential and kinetic energy. So the center of mass has the same amount of mechanical energy at the end of the step as it had at the beginning. It's just that it's moving in the wrong direction toward the ground, right? And this is where the other leg comes into play. So when the other leg hits the ground, the two legs work together to redirect the center of mass from that downward motion into an upward arc that it needs for the next step. Now, the center of mass does lose some mechanical energy during step-to-step transition, but the energy that's lost is resupplied by the push-off force from the trailing leg, so the next step looks a lot like the previous one, giving us a stable gait cycle. This way of thinking about human locomotion has its origins in the study and development of passive dynamic walking machines, which are these unpowered robotic bipeds that are capable of walking unassisted and uncontrolled down shallow slopes. And the insights that were gained from the study of these artificial walkers led to the development of the dynamic walking approach to human locomotion, which, among other things, has helped us to understand how the remarkable efficiency of human locomotion derives from the ability to exploit the physical dynamics of the body. But the environment doesn't always cooperate, right? When the terrain gets a little bit more interesting, just letting the foot land where it naturally wants to go just might not be an option, right? Instead, the walker has to identify potential footholds and modulate gait to land on those footholds. And this entails some kind of neuromuscular intervention that interferes with the passive trajectory of the body. But there are all kinds of ways in which one could alter the trajectory of the body, and some of these are better than others. What we have found is that the dynamic walking perspective offers some useful insights into the right and wrong ways to control a physical system with the structure of a human body. So to kind of anticipate where we're going with this, the kind of right way, at least from the standpoint of stability and efficiency, is to do this: to initialize the mechanical state of the body prior to the beginning of each step so that the foot will land on the next target by following its natural pendular trajectory. This requires visual information from more than one step ahead, but it allows walkers, or would allow walkers, to negotiate complex terrain in the same way that they walk over flat, obstacle-free terrain. That is, by harnessing rather than ignoring or fighting against the forces that are acting on the body. So the experimental paradigm uses an LCD projector to project virtual obstacles onto the floor. And the obstacles appeared as blue squares of light that were randomly distributed along a walking path. The subject's movements were tracked by a motion capture system, and the mocap system and the projector system were integrated to allow us to do things like detect when subjects stepped on the obstacles. The subject's task was to walk from a start position to a goal at the other end of the path without stepping on any of the virtual obstacles. Now, we're interested in knowing how far ahead along the future path walkers need to be able to see. So we created a traveling window of visibility centered on the subject's head and kept obstacles invisible until they fell within that window. Okay, you get the idea. The size of the visibility window ranged from 1 to 5 step lengths, and there was also a full vision control condition in which the entire obstacle field was visible throughout the entire trial. So on to some results. On the top, you see walking speed, and in the bottom, number of collisions, number of steps per trial on which the subject actually landed on an obstacle. So I'm not going to go through these plots in great detail because you really just need to know two things. First of all, subjects walked slower and were more likely to step on obstacles as the visibility size, window size decreased, as you would expect. But second, and more importantly, the most significant changes were found when vision was restricted to less than 2 step lengths ahead. So why 2 step lengths, right? Why not 1 step length or 3 step lengths? John Mathis, a former graduate student in my lab, now a postdoc at UT Austin, proposed a really elegant explanation for these findings. And what I think is so exciting about John's explanation is that it suggests the following, that the tendency to use visual information from up to 2 step lengths ahead is rooted in the biomechanics of bipedal locomotion. So here's John's explanation. Recall that during the single support phase, the body is mechanically similar to an inverted pendulum. The trajectory that the center of mass will follow in the absence of muscular intervention depends primarily on 2 factors: the position of the planted foot, which defines the base of the inverted pendulum, and the initial position and velocity of the center of mass at the beginning of the single support phase. Note that these 2 factors are fixed at the onset of the single support phase, right? So by the time the toe leaves the ground, the passive trajectory of the center of mass, that is the trajectory that it would follow in the absence of any muscular intervention, is completely determined. Now, if obstacles are present, and if the walker can only use information from 1 step length ahead, what that means is that obstacles that are located in the vicinity of where the foot will land may not be visible until after the passive trajectory of the center of mass is determined, right? So in this situation, the only thing that the walker may be able to do to avoid stepping on an obstacle is to make a mid-flight correction that interferes with the passive motion of the body. All right, so this could explain why walking performance was affected in our experiment when subjects could only see 1 step length ahead. However, if subjects could see a step and a half ahead, then they may be able to adjust the push-off force from the trailing leg to kind of redirect the center of mass away from obstacles and toward a safe foothold. And if they can see at least 2 step lengths ahead, they may also be able to adjust the position of the planted foot, which again defines the base of that inverted pendulum. So this could explain why walking performance improved in our experiment when visual information from further ahead became available, right? So essentially, what this means is that subjects have a more effective means of control, right? When they can see further ahead, sufficiently far ahead, then they are able to adjust the position of the planted foot and redirect the center of mass with the push-off force. And what they're doing is essentially initializing the state, the mechanical state of the body, right, so that the foot and the body can just follow that natural trajectory to the target from that point forward. So this leads to the following prediction, that 2 step lengths of visual look ahead should be sufficient to allow walkers to exploit their inverted pendulum-like structure. To test this prediction, John built a simulation of an inverted pendulum in 3D. He then fed the initial position and velocity of the center of mass at the beginning of each step into the simulation and ran it forward for a duration equal to the actual duration of that step. So the blue curve is the trajectory based on the passively falling inverted pendulum model, and the red curve is the actual COM trajectory. John then measured the distance between the endpoints of these two trajectories in 3D. Okay, and the smaller the distance, right, the more similar the subject's movements are going to be to a passively falling inverted pendulum. So we think of this as a kind of indirect measure of how efficiently the subjects are exploiting their inverted pendulum-like structure. So here are the results. On the y-axis, this is that distance I just referred to, right? So the distance between the endpoints of those two trajectories, and it's normalized against the values that were obtained in an obstacle-free control condition, right? So subjects walked with no obstacles in the way. In the full vision condition, the value is around 1.09, which basically means that subjects were less like an inverted pendulum in this condition than they were when there were no obstacles in the way, but only by a little bit. And as the visibility window size decreased from 5 step lengths down to about 2 step lengths, there's not much of an effect until visibility window size decreases below 2 step lengths, at which point the difference between those two trajectories begins to spike. Okay, so when obstacles don't appear until they lie within 2 step lengths, walkers' movements are less like an inverted pendulum. And this makes sense, right? Because what it means is that the obstacles are not visible until after one or both of the two determinants of the passive COM trajectory are set. And the only thing that the walker can do is make a mid-flight adjustment to intervene and adjust the trajectory of the COM. But with 2 or more step lengths of visual look ahead, then obstacles become visible while the two determinants of the passive COM trajectory are still under the walker's control, right? So the walkers are able to then exploit their inverted pendulum-like structure as well as they can when vision is unrestricted. Okay, so now that we know something about how far ahead visual information is needed, we can turn to the question of when visual information is no longer needed, right? So do walkers need visual information about the location of a target all the way through the step, right? Or can they achieve comparable levels of stepping accuracy even if that information is not, even if they stop sampling that information partway through the step, or perhaps before the step is actually initiated? Again, thinking about this question from the dynamic walking perspective motivates a hypothesis. If walkers initialize each step and then follow a ballistic trajectory to the target, then visual information about the target should be unnecessary once the step to that target is initiated. So in this experiment, subjects walked across a path of small targets that were positioned like stepping stones. And they performed this task in a full vision condition, which is what you're looking at here, in which all of these targets remain visible throughout the entire trial, as well as in a variety of kind of invisibility trigger conditions in which targets turned off partway through the step. So it looks something like this. Okay, so this is actually a 0.5 trigger condition. So the targets are turning off when the foot is halfway on its way to the target. Okay, and so we tested a variety of different trigger conditions. There were 8 in all, and there was also this full vision condition in which the targets were visible throughout the entire trial. So in this full vision condition, stepping accuracy was about 36 millimeters. So this is baseline performance. And in these next 3 conditions, stepping accuracy is not affected. The targets the targets are visible until the point where the step is initiated, and they become invisible at various points in time during that step. But notice that stepping accuracy is not affected. When targets disappear shortly after the step is initiated, stepping error increases slightly, but there's not much of an effect. It's a small difference there. When the targets disappeared toward the end of the previous step, then we start to see an increase, a pretty substantial increase in stepping error, and this upward trend continues as the targets disappeared earlier and earlier. So visual information about the location of targets is most important up until the point where the step is initiated, right? Once the step is initiated, once the toe leaves the ground, removing visual information about the location of that target has a negligible effect on the accuracy of stepping. And this is consistent with a strategy of using information in advance to initialize each step and then allowing the body to follow its natural pendular trajectory to the target. In other words, a strategy that kind of minimizes the role of active control during the step. Okay, so we know that visual information about the target is not necessary after this point. And from the first experiment that I told you about, we know that walkers need to see visual information about the upcoming terrain before this point right here. So putting these two results together leads to the following hypothesis, that there's a kind of critical phase for the visual control of stepping. For a target at the end of step N, this critical phase takes place during the last part of that previous step. And this makes sense, right? Because this is the point in the gait cycle where the walker is best able to use visual information to initialize the state of the body for the upcoming step, which minimizes the need to intervene with the natural pendular trajectory. So to test this critical phase hypothesis, we kind of combine the manipulations of the first two experiments. Subjects walked over a series of small targets that did not appear until they fell within a threshold distance of subjects, and then subsequently disappeared once they fell within a second closer threshold distance. So it looks something like this. And this manipulation was applied to each and every target in the sequence with the exception of the first two. Now we tested a handful of conditions with various triggers for the invisibility and visibility triggers. And so targets were visible during the predicted critical phase in some conditions and not in others. So in this graph right here, I'm going to use these horizontal bars to illustrate both the manipulations and the results. The width and the position of each bar in this graph indicates the duration and the period of time during which each of these targets was visible, right? So in this particular condition, targets first became visible when the subject was a step and a half away from the target, and then disappeared when the subject was one step from the target. Okay, so this is the condition in which targets were visible during that predicted critical phase and only during that predicted critical phase. And then the height of the bar in the graph indicates the mean stepping error. So in this condition, about 43 millimeters. So let's compare this condition with three other conditions in which targets were visible for twice as long, for a full step, right? Either during, before, or after the predicted critical phase. Notice that when targets are visible for an entire step that includes the critical phase as well as half a step before that, stepping error is not significantly better. Okay? And when targets are visible for an entire step, but before or after the predicted critical phase, stepping error is significantly worse. And what I think is so interesting about this result is the fact that targets are visible for something like 250 milliseconds in this condition, right? This condition here, okay? So even a brief glimpse of a target is sufficient to support accurate stepping as long as that information is available at the precise moment that it's needed to initialize the upcoming step, as long as it's available during the critical phase. Okay, so let me wrap things up here. When we walk over complex terrain, we have to make gait adjustments to accommodate obstacles and irregularities in the locations of target footholds. But that does not mean that each and every detail of the movement has to be actively controlled, right? Active control is needed only to kind of tweak the mechanical state of the body so that the movement can be largely under passive control. This tweaking is based on visual information about the upcoming terrain, and it happens during a specific part of the gait cycle, the latter part of the previous step. This is the critical phase for visual control because this is when the two variables that determine the passive COM trajectory are under the walker's control. Once the step is initialized, the walker can simply allow the body to follow its natural passive trajectory to the next target. And because there's no need to actively steer the leg during this phase, the walker can begin to use information about the next step, right? So that step can also be completed under passive control. And this cycle of passive control, occasionally interrupted, occasionally punctuated by brief intervals of active control, continues on and on, allowing walkers to negotiate extended stretches of complex terrain with a degree of efficiency and stability that closely resembles what's possible in flat, obstacle-free terrain. So I'll stop there, just some acknowledgments. Again, it was John Mathis's insights about how to bring the dynamic walking perspective into the realm of complex terrain that was really a breakthrough for this project and opened up lots of doors. And Sean Barton has taken over where John left off. So I'll stop there. Thank you.